Well, now here's a great example of simple harmonic motion. In fact, it's one of the most basic that you ever come across. I've got a rotary motion probe. Well, this is the first time I'm doing this one, so let's see how it works. I've got a rotary motion probe, and here is a pendulum. Classic. I've got it down on a wire and a little 200 gram mass, 0.2 kilogram mass, and it'll go back and forth, and the idea is that hopefully I should be able to see some periodic motion through this motion sensor. I've got it set to read angles. I'm going to zero it out as is. No, not calibrate. Zero out. I'm going to change the duration to 60 seconds. Gives me plenty of time. Okay. And we'll graph this out. And let's see. Nothing ventured, nothing gained. So we're expecting a nice sinusoidal wave back and forth of some value. Let's see. Make it drastic enough that it'll go. Well, physically it certainly is simple harmonic motion. 1, 2, 3, 4. And we could actually graph out the amplitude versus time. We could graph out total energy versus time. We could graph out any of those parameters. So take a look. The rotary motion probe is actually going back and forth pretty nicely. Let's see what our graph looks like. Oh, looks like if we zoom in there, we'll get something nice. All right, let's stop it. Oh, very good. And actually, it's interesting because this graphed out angle. Right, so that's the angular displacement, or rotational displacement, if you will, versus time. And then there's the rotational, or if you will, angular velocity over time. And let's just choose, the angular displacement. Zoom in. Yes, we get a very nice graph there. There's some cutting off. And it corresponds to the velocity change, but overall, a very nice graph. Again, looking at the top graph, which is angular displacement, the actual radian value, it's not in degrees but radians, through which this is turned. If it were to go around and around completely, then we'd see slightly different values, but very cyclical, very nice.